Alright, so we're getting into chapter 2 now, which is basic introductory chemistry. Don't get too overwhelmed by this chapter. I know it's a lot of material. I know a lot of you don't have a chemistry background, but just take the basics away from this chapter and you'll do fine moving on from here. So to start with the basics, as I said, when we're talking about chemistry, we're talking about matter. Basically, matter is anything that has space and has mass. Anything that's made of atoms is considered matter. And of course, there's three states: a solid, a liquid, and a gas. And I assume you're familiar with those basic states of matter at this point. Of course, matter undergoes physical changes as well as chemical changes. The physical changes would be like when the solid goes to a liquid, or when a liquid goes to a gas. A chemical change would be where the actual molecules are changing composition. So this would be like the Statue of Liberty oxidizing over time. That would be an example of a chemical change. There's two things that exist in the universe as far as we know. One of them is matter. We just mentioned that. And then we get energy. Energy is the ability to do work. So this is actual movement, would be considered kinetic energy, moving your body, moving atoms and molecules around, whereas potential energy is more like stored energy. Think about a pen. If you have a pen in your hand right now, you hold it straight up in the air, that pen now has potential energy. It has the potential to fall straight down on the floor. If the pen's just laying on the floor, it doesn't have any potential energy anymore because there's no forces acting upon it, right? Gravity is going to act upon that pen when it's up in the air, which is why we say it has potential energy. When a dam is holding back water, we say that it has potential energy. When that water starts to trickle through a little bit, it's releasing some kinetic energy that is then captured and then used as a power source for many people, right? How many of us get our energy from like the Conowingo Dam or a local reservoir? So energy can be converted between kinetic and potential energy, but ultimately all of the energy in the universe is can never be destroyed. That's all held within something called the law of conservation, which kind of goes beyond this class. There's some different types of energy: mechanical energy, which is used in actually moving things; chemical energy, when we're talking about bonds, chemical bonds between atoms. There's electrical energy, and then radiant energy would be like the type of energy that we use when we're cooking, right? Heating up our food in a microwave, or the type of energy that we feel when we feel the sunlight, that UV light, is called radiant energy. The most common types of energy that we're talking about in a biological sense is that chemical energy, converting the chemical energy in the food that we eat to a type of chemical energy that our cells can use. And that's this molecule that's written right here, ATP. So we're literally taking the potential energy from the food, between the molecules in the food that we eat, and converting it into this molecule called ATP, so that our cells can use this ATP to do stuff, to blink, to breathe, to move, etc. So that's kind of where we're going with this information. Talking about matter, and we've kind of hit on chemistry just a little bit when we talked about the biological levels of organization. But of course, these chemical elements are the basic building blocks of matter. We can't break them down any more than they already are, right? An atom is an atom. Once you break down all of the atoms, basically all you have is a bunch of protons, neutrons, and electrons. But once you start arranging those protons, neutrons, and electrons together in different ways, you're going to get the different elements. Ultimately, there's about 26 different types of elements in our body. We mentioned 6 of them last lecture. Those element names are abbreviated into letter symbols that we mentioned, right? C for carbon, etc. Here's the majority of the elements in our body. As we mentioned, the majority of those elements are carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. And here you see them. Calcium is another one. But again, that's still less than 3% of our total body's chemical composition is calcium. The majority is, of course, oxygen and hydrogen in the form of water. Carbon is the majority of our proteins, as well as nitrogen. And then there's some trace elements in there, some iron, some iodine, some zinc, etc. So atoms, of course, as I keep alluding to, they're the smallest units of matter, made of protons, neutrons, and electrons. Protons are the positive charge, that positive charge. Neutrons are neutral, Those are also within the nucleus. And then the electrons are negatively charged particles. Atoms are electrically neutral if they have the same number of protons and electrons, because the positive charges equals the negative charges. So the overall charge would be 0. Here you see a little picture of an atom. So they have a nucleus, just like the nucleus of our cells, which some of you may already be familiar with. The idea that it's a central location, and that central location is where all of those protons and neutrons are, and then kind of in a cloud or in orbits, so to speak, around our nucleus would be our electrons, and that's where all of the energy within our atom is stored. The atomic number is assigned to every element, and that's literally the number of protons within the nucleus. So a element that has atomic number 1 only has 1 proton in the nucleus. An element that has atomic number 2 has 2 protons in the nucleus. The mass number is equal to the number of protons and the number of neutrons within the nucleus. So if the mass number is 4 and the atomic number is 2, we know that there are 2 protons in the nucleus and 2 electrons in the nucleus, because 2 plus 2 equals 4, which was the mass number. The periodic table of elements lists all of the specific information in terms of atomic number and mass number for all of the elements. Here's some of the common ones. Again, you don't really need to know these or have these memorized. You just need to know what these numbers represent. So here, for instance, atomic number 7, nitrogen, has 7 protons in the nucleus. That's what that P is. 7 neutrons in the nucleus. And then if you count them up, there are also 7 electrons outside of our nucleus. That makes our atomic mass 14, because that's the number of protons, plus the number of neutrons. An isotope is kind of like an exception to that rule. For the most part, our elements have the same number of protons and the same number of neutrons. Just flipping back here briefly, you saw 7, if we just look back at nitrogen here, 7 protons, 7 neutrons, 8 protons, 8 neutrons in oxygen, 6 protons, 6 neutrons in carbon. Well, isotopes have different numbers of neutrons. They have the same atomic number, so in other words, they have the same number of protons, but they'll have a different atomic mass. This can make our elements radioactive, in which case we call them radioisotopes. They can be used in diagnostic medicine, cancer therapies. If you've ever heard of radiation therapy, that's all related to these radioisotopes, or these unstable isotopes of atoms. And literally all that means is that there's a few extra neutrons in that nucleus. So here you see what I mean. These are the isotopes of hydrogen. Hydrogen actually usually does not have any neutrons in the nucleus. It's just a single proton in the nucleus. But if we add a neutron, that's the blue circle here, so now we have the atomic number is still 1, but now the atomic mass is 2 for this isotope. We've created a isotope of hydrogen called deuterium. And then if we add another neutron to our nucleus, now we have an atomic mass of 3. Tritium is still 1 proton. No matter what, all of our hydrogen isotopes have 1 proton. They just have different numbers of neutrons. Same number of electrons, still 1 electron, but just a different number of neutrons. That's what makes it an isotope. Those electrons, we haven't mentioned those yet. Those are those little black dots that were floating around the outside of those atoms that we were just looking at. They like to hide in something called an electron shell, and those shells are basically equivalent to different levels. Some of them like to be very close to the nucleus, and some of them like to be further away from the nucleus. The valence shell is the outermost electron shell. So in other words, the electrons that are furthest away from the nucleus are called the valence shell electrons. Those electrons are the ones that are going to determine how that element reacts with other elements, or how that atom reacts with other atoms. Is it going to bond with them? Is it not going to bond with them? Is it going to steal electrons? Is it going to donate electrons? That's all determined by those valence shell electrons. the maximum number of electrons that can be in that valence shell is 8. So most atoms want to have 8 electrons in their valence shell. If they don't, then they're going to want to bond with other atoms so that they can create a situation where they have 8 electrons in their valence shell. Let's take a look at some examples. Atoms are going to form those chemical bonds when those electrons are exchanged between them, and those chemical bonds formed when those valence shells are interacting between specific atoms. And this is what I was getting at when I was mentioning that 8 valence shell electrons. It's called the octet rule. Atoms are going to form bonds with other atoms until they reach 8 outer electrons. The only exception to that is hydrogen, which can actually only hold 2 electrons instead of 8. But all of the other ones want to hold 8 in their valence shell. Here's a little video summarizing the basics of atomic structure and the basics of chemical bonding. You can check that out in your own time. There's a special type of bond called an ionic bond. In an ionic bond, those valence electrons are either donated or accepted from other atoms. So an atom, say, that has 2 outer electrons, instead of trying to steal 8 electrons from, or 6 electrons from other atoms so that it can achieve its octet, its 8 valence electrons, it's just going to give up those outer 2 electrons and say, here you go, you can have these 2. In that case, a neutral atom that gives away 2 negative charges is now going to become a positively charged atom because it's now less negative. It's given away 2 of those negative charges. So it's called a cation. A cation is a negatively charged ion. The atom that receives those 2 electrons that were just given away by that other atom is now a negatively charged atom, and it's called an anion. So the cation is a positively charged ion, an anion is a negatively charged ion. I remember that because I like cats, and cats are positive, so a cation is a positive ion. The word anion kind of looks like the word onion, and I don't like onions, so that's a negative thing. Anions, or onions in this case, are negatively charged. Hey, if it works, use it. If it doesn't, just forget I said it. Here's a little summary of what I was telling you about the ionic bonding. Here you see sodium. Sodium just has 1 valence electron, so instead of trying to steal or borrow 7 electrons from other atoms, it's just going to donate that 1 outer electron. It's actually going to donate it, in this case, to chlorine. Chlorine has 7 valence electrons. Here you can see 1, 2, 3, 4, 5, 6, 7. So it only needs 1 more electron in order to be nice and happy. So it's going to take that extra electron from sodium here, stick it into its outer shell. So now chlorine has 8 in its outer shell. And look, so does sodium now because it gave up that 1 valence electron. So sodium now has 8, chlorine now has 8. But if we look at these ions in total, sodium still has 7, sodium now has given up 1 of its negative electrons, so it now has a positive charge. That's our cation, whereas chlorine now has a negative charge because it has accepted an extra electron. The molecule is what's formed when those 2 atoms are sharing electrons. When we were talking about ionic bonding, like in this slide, we were giving up or receiving electrons, so there wasn't really a molecule formed, it was just an ion that was formed in an ionic bond. In the case of forming a molecule, these atoms are now going to share electrons. So an example would be something like oxygen. Oxygen is never just by itself, it's always bound to itself in a molecule called O2. So 2 oxygen molecules bound together, or CO would be carbon monoxide. That would be another example of a molecule. In this case, it's called a compound because it's made of 2 different elements. Oxygen itself is not a compound because it's the same element, O2. It's just 2 oxygen atoms, whereas carbon monoxide is an atom of carbon and an atom of oxygen. The molecular formula is something that you may be familiar with already. Basically, that little subscript next to the H, that little 2, is representing that there are 2 hydrogen atoms, and the 1 is implied next to the O here. So in a molecule of water, we have 2 hydrogen atoms and 1 oxygen atom to create 1 molecule of water, H2O. The 1 is an implied number here next to the O. And what this tells us is the oxygen is sharing electrons with the 2 hydrogen atoms to make a water molecule. It shares in what's called a covalent bond. A covalent bond is literally sharing between 2 atoms. The higher number of covalent bonds, the more strongly those atoms are bound together. So in this case here, we see nitrogen, for example, in the molecule N2. There are 3 bonds between the 2 nitrogen atoms. So those 2 nitrogen atoms are held together very, very strongly. Whereas something here, we just have a single bond between our 2 hydrogen atoms, is not going to be quite as tight as these triple bonds between our nitrogen atoms. Here you can see the molecule CH4. This is a molecule of methane. 1 carbon, 4 hydrogens. Each hydrogen is going to share its outer electron with carbon, and now carbon has 1, 2, 3, 4, 5, 6, 7, 8 outer electrons. Remember, hydrogen was the exception to that octet rule, only needing 2 outer electrons. Every hydrogen atom has 2 outer electrons, so that molecule is nice and happy. Here we see a water molecule, our H2O, our 2 hydrogens are sharing their electrons with our valence electrons on our oxygen. Oxygen now has 1, 2, 3, 4, 5, 6, 7, 8 outer electrons as well. Now, covalent bonds are not created equal. As you may see here, our water molecule is actually a bent, whoa, sorry about that, my mouse got away from me. Our water molecule, okay computer, please be nice to me. Sorry guys. So if we look here, our water molecule is actually a bent molecule, and you see these little squiggly lines, positive and negative. That's actually telling us that it's a polar molecule. What that means is that the oxygen and hydrogens are not sharing those shared electrons equally. In fact, because oxygen is such a larger molecule, it's going to have those shared electrons for a longer period of time than that hydrogen has those shared electrons. Because it's such a larger molecule, it takes those shared electrons longer to go around the oxygen than it does just to zip around the hydrogen. So these shared electrons are around the oxygen longer than they're around the hydrogen, which gives oxygen a slightly negative charge and hydrogens a slightly positive charge, which makes water a polar molecule. So the type of bond in a water molecule is called a polar covalent bond because of the unequal sharing of those electrons. And they're shared unequally because that oxygen is such a bigger molecule than the hydrogen is. Oxygen is just a bigger atom than the hydrogen atoms. The hydrogen atoms are very, very small. Oxygen is like 8 times the size of a hydrogen. A nonpolar covalent bond would be equal bonding between molecules. And here you see some examples of nonpolar covalent bonds. The bonds that I mentioned, those triple bonds between the nitrogen, the single bonds between the hydrogens, and our carbon-hydrogen bonds in the methane molecule. Those are all nonpolar covalent bonds. The electrons are shared equally in all situations. A hydrogen bond is another type of bond that we talk about in chemistry, and specifically in biochemistry. A hydrogen bond is literally when there is a bond in between molecules as opposed to between atoms. So in this case, a water molecule is attracted to another water molecule. If you recall, I'll just flip back here briefly. Take a look at our water molecule here. There's a negative side and a positive side. Well, the positive side of this water molecule may be attracted to the negative side of another water molecule. That would create what's called a hydrogen bond. Hydrogen bonds don't necessarily involve hydrogen, but they usually do. Hydrogen bonds are responsible for that surface tension on water. These are also found within DNA and proteins. Here you can see what I was alluding to, our water molecule here, with all of its positive and negative sides, maybe being attracted to specific anions or cations in this situation. Notice the oxygen is going to point towards our sodium, and the hydrogens are going to point towards our chlorine, because positive and negative charges attract, like charges repel. So our positive hydrogens are going to like the negative chlorine, and our negative oxygens are going to like our positive sodium. So they're going to surround the sodium and chlorine differently, which is why salt dissolves so nicely in water. And here you can see hydrogen bonds forming between adjacent water molecules, the positive hydrogen being attracted to the negative oxygen of a different water molecule. And here's a nice animation summarizing chemical bonding for you. A free radical would be an unpaired electron wanting to kind of steal or be destructive to a neighboring molecule. Free radicals break apart other molecules, they dissolve substances. Free radicals are responsible for the aging process. Free radicals can be responsible for diseases. Our body tries to minimize free radicals by trying to basically gobble them up when our body comes in contact with them. Or if free radicals are produced by a metabolic process, our body tries to get rid of them very quickly. Some examples of processes that can generate free radicals would be UV exposure, some metabolic reactions as I mentioned, as well as other harmful substances such as air pollution that could strip electrons from some of the molecules within our body. Some diseases caused by free radicals: atherosclerosis, that's the hardening of the arteries, Alzheimer's, emphysema, diabetes, rheumatoid arthritis, all related back to free radical damage. Antioxidants, you've probably heard of them before, lots of zinc, vitamin C, vitamin E, those are all free radical fighters. You get them from fruits and vegetables, so eating your fruits and vegetables helps to combat some of those free radicals that accumulate from day-to-day processes. Overall, chemical reactions happen in our body as bonds are breaking and new molecules are forming. That energy is being transferred from one form to another. It can be captured in other molecules, or it can be released in the form of heat. So our body's always trying to build structures or performing specific functions like metabolic reactions. That's all involving chemical reactions. There's different types of chemical reactions. Anabolic reactions are building reactions. Those are when molecules are being synthesized or proteins are being synthesized. A decomposition reaction is where molecules are split apart. Those are also called catabolic reactions. Think of the word catastrophe, means to destroy. So in this case, a catabolic reaction is a decomposition reaction where molecules are literally splitting apart. There can also be exchange reactions where different molecules are exchanging parts ultimately to create new products in the end. And some chemical reactions are reversible. They can go in one direction and then reverse themselves and then go in the other direction to create or break molecules. Here you can see some of those things I was just talking about. The synthesis reaction up here in the top right corner, where A and B combine to create A and B, whereas a decomposition reaction would be where the molecule AB breaks down to form A and B. An exchange reaction, in this case AB and CD, create AD and BC. And then the reversible reaction, where you have AB creating A plus B, and then A plus B creating AB, kind of back and forth reaction. And there are specific examples of each of these reactions listed as well. Here the example of ATP breaking down to ADP is a very important reaction that we're going to be familiar with later. So this animation goes through the different types of reactions and how they play a role in our overall equilibrium. I'm going to stop here for right now. We'll pick up with water and organic molecules in the next part of this lecture.